Okay, now we're going to use the calculator to find a regression line and a regression exponential equation to fit some real-world data. So we're studying a population of some animal, and we have the following years and population numbers. You're going to notice the data are not evenly spaced. We have 95 to 97 is 2 years, 2 years, 3 years, and 1 year. This doesn't matter to us if we're going to use regression. So we're going to find a line and an exponential, and then we're going to predict the 2012 population from both of those. We're also going to answer the question, when was the population 100, from both of the models. And perhaps we can choose which of the models actually fits the data better once we get a look at it. So the first thing we need to do is put the data in. To do that, we start by pressing Stats, and then we will select Edit. Now, I've already taken the time to type the data in, so you don't have to watch me just type away. And I've made one selection. I've decided to let year 2000 be x equals 0 rather than type in entire large year values here. So 97 went in as -3, being 3 years before year 2000, and so on through the list. 2009 is 9. We should identify that in our model. X equals 0, the same as year 2000. Okay, so now let's find the equation of a line. I press Stat, and I move to the right to make it on Calculate. And in here we can find various regression equations, a whole bunch of them. The one we're interested in first is linear regression. It pops me back to the regular screen, and now I run it by pressing Enter again, and I get the equation of a line. The equation is ax plus b with the given a and b values. I'm going to round those off just a bit for convenience writing them. 1.5x plus 63.95. So we see the population is increasing at 14.15 per year. And in year 0 it would have been 63.95, with 0 being 2000, which sort of makes sense in between those two numbers. We also get something called an R value, and that's talking about how well the line is fitting the data. 0.908 is a strong positive correlation. Values closer to 1 are better, closer to -1 would be negative correlation. But around 0 tends to indicate no correlation at all. Let's take a look on a graph. Now I have to do two things. I have to put the equation in, so I go to y equals, and I could just type in the equation. But a better method to know, particularly when we start doing logistic models and other longer equations, is to how the calculator can put it in itself. By pushing variables, number 5 is statistics, and moving to equation, the first choice is regression equation, and it will simply type in the exact equation we just found. Now I'm going to graph this, but I also want to see my data. And we see up here plot 1, plot 2, plot 3. Those are stat plots. I want plot 1 turned on. So I'm going to go to second stat plot, and I'm going to enter this and select on. Also going to make sure that the X list is L1 and the Y list is L2, which corresponds with the data that I typed into the calculator. Okay, so now I'm ready to graph. And a quick way to graph, we could set the window in order to be able to see our data, but I can also just go zoom and go to zoom stat. If I'm not happy with this window, I can change it later, but this is a very quick way to see a stat plot. So it has selected a window to see all of my data points, and of course then I get the line corresponding. It's there, it's not bad, but it looks to me like the data is curving up more, so perhaps we have exponential population growth. So let's find an exponential model, and then we can compare both of them. So once again, I select Stat and move over to Calculate. And this time, instead of linear regression, I'm going to select exponential regression. It comes back out, I run it again, and I get my exponential model. This time it's a times b to the x. A is 61.52, rounding it off. B is 1.139998. Let's go 1.4 for rounding off purposes to the x. And so now I have an exponential model, y equals this, and a linear model up here. Let's take a look at this one. So I press y equals, and to compare the two, I'll put it in the y2 position. The same procedure. I press variables, number 5 for statistics. I move to equation, and now we'll have both of them on the plot. So we can look at both graphs and decide which one is better. As the calculator graphs it, it does seem like the exponential is perhaps truer to our data. It seems to be closer almost all the time than the line is. You'll notice particularly these 2 points, the exponential is much better. The last point, it's moving in that direction, and it catches the first point better. Quitting this, I didn't note it earlier, but R was 0.97, so we actually have a higher R value, which tends to be indicative of a better fit to our model as well. Predicting the population in 2012. Okay, year 2000 is x is 0. That's the same thing as saying x is equal to 12. That might not be in my window at the moment, so I'm going to press window. I see that in fact my x mins and maxes x equals 12 will not work. So I'm going to change this to say 15 and regraph my plot. Just added a little bit more space on this end for these calculations. Predictions off of the data are called extrapolation, and they're not necessarily the most accurate thing one can do in life. But this question asked for it, so we're going to see what answers we get. So I'm going to do second calc. Value allows me to plug in an x value. I'm going to plug in x equals 12. And on the line, the equation of the line is typed out here, and it's blinking on the line. It's giving me a value of 233.7. Now, I don't know if I like that prediction terribly much because it's lower than the population actually was in 2009. If I press up, I continue to have x equals 12, but I've moved up to the exponential equation. And I'm off of my actual graph, 296.36. So we can use up and down arrows to move back and forth between the two graphs. Now I want to answer the question, when was the population 100? We can't just type in a y value equal to 100, but what I can do is go to y equals and make a third graph of 100. And this third graph of y is a constant 100 will intersect both of the other graphs, and that intersection point in each case is what I'm interested in. So second calc, I move to number 5, the intersection. First curve, this time it's the line, so I identified it's the line. Second curve, it has the exponential. I'm not interested in intersecting the line and exponential. I'm interested in the line intersecting y3 is 100, which is typing up here. Guess, not terribly important because there's only one intersection, and I'm getting x equals 2.548 for the intersection point between the line and that. So that would be 2.5 years after 2000, or 2002 and 0.548, maybe around June. We could figure that out more accurately if we're interested in it. And to find the intersection between the other curve, now it's on the line. I can see that even though it may not be clear in your view, it puts the equation of the line here. So I'm going to move, grab the exponential, and it put up the third, the y3 equals 100. And I'll let those two intersect. And so this was for the line. For the exponential, I'm getting 3.707. So it's predicting that we would have a population of 100 in 2003.707. So both of those are somewhat interesting predictions because we can see that the data was still at 92. Well, both of the exponential curve in particular is staying lower than the line, and the data is growing faster at the end. So it is a curious result.